Hello everyone, myself Rupam Maiti, currently studying at National Institute of Technology Durgapur, majoring in electrical engineering. I welcome all of you to my channel. Let's learn together. So, today I'm going to give a brief description of one of the most fundamental concepts in electrical systems, that is power factor. Okay, in this presentation, we are going to look what is a power factor, different types of power in AC systems, okay, and give and take some basic examples from our daily life and compare it with this concept of power factor. We will also see what is a poor power factor and how to fix a poor power factor, and finally we will have a brief summary of this presentation. First thing first, what is a power factor? Right, power factor is nothing but the measure of efficiency in electrical systems. Right, in this world, nothing is 100% efficient. We always try to measure the efficiency of any systems. In electrical systems, we have power factor. Mathematically, we can say that power factor is the ratio of real power upon apparent power. Right. There are three different kinds of power we will be looking a bit later. So the ratio of real power and apparent power gives us the power factor. As it is a ratio, so it is a dimensionless quantity. Fine. And we see that the power factor values ranges from 0 to 1. Means power factor, when the value of power factor is equals to 0, it means least efficient, and when the value of power factor is equals to 1, it means most efficient. Clear? I have told that it is the ratio of real power and apparent power. There is one more kind of power in AC systems, that is reactive power. Clear? And this reactive power comes into context when there is phase difference. Phase difference between between current and voltage, right? Let us go into some details. So I was talking about the phase difference. Let us see the relationship between voltage and current in case of an inductor and capacitors in AC systems. In AC systems, right? Suppose we have an inductor connected to an AC supply voltage. Let the voltage across the inductor be VL and the current in the circuit be IL. Then we can say the current IL lags the voltage by lags the voltage. Which voltage? voltage across the inductor by 90°. We have to keep this in mind. Okay, if we draw the phasor diagram, it looks like this. If we have here current IL, the voltage is leading by 90°. So this is the scenario. On the other hand, if we have a capacitive circuit connected across an AC system, an AC supply, let the voltage across the capacitor be Vc and the current in the circuit be IC. Then we can say that the current IC leads the voltage Vc by 90°. Okay, and if we try to draw the phasor diagram, it looks like this. Here is IC and here is Vc. This is 90°. Fine. In case of resistors, the current and the voltage are in phase. So the reactive power term comes only in case of inductor and a capacitor. Okay. Now we have talked about this, that there are three different kinds of power in AC systems, that is real power, reactive power and apparent power. Suppose we have an electrical circuit like this, where we have electrical circuit like this, where we have a resistor of R, an inductor of impedance XL and a capacitor of impedance XC connected across an AC supply. So what do you mean by real power then? Real power is the actual work done. Actual work done. Okay. The actual work done is measured in terms of real power. What is reactive power? The power stored in reactive components. Reactive components. Clear? The mathematical definition says that the real power can be calculated is equals to I square into R, only the value of the resistance. The reactive power, on the other hand, is occurring only due to the reactive components, so its value can be measured as I square into X, reactance, where X is the reactance. Its value is nothing but JXL minus JXC. Okay, its mod value. And the apparent power is the phasor sum of real power and reactive power. So its value would be I square Z, where Z is the net impedance of the circuit. Net impedance. Clear? And mod Z's value is nothing but given as R square plus XL minus XC square. Clear? In this way, we can calculate these three kinds of power. Now let us understand better with the help of an example from our daily life, the beer analogy. It is one of my favorite analogies and it clearly explains the concept of three different powers in AC systems. Suppose we ordered a glass of beer. The glass has these two components, the real beer part and the foam part. And we pay by the glass, whole glass. But actually we don't. This is useless. Foam part is useless and actual part is the beer. Okay, so we can relate like this, that foam is the reactive power and beer, which actually matters to us, which actually does the work in electrical system, should be the real power. And we are paying by the glass, so the sum of reactive power and real power is the apparent power. Clear? We look at the units. Reactive power unit is var, volt ampere reactive. Real power's unit is watt as usual. An apparent power unit is volt ampere VA. Fine. A second analogy more relatable to us, that is the Lay's packet analogy. If we have a packet of Lay's like this, we know that the whole part is not filled with chips, right? A major part is filled with air. So the air inside it can be related, the air can be related as reactive power. And actually, which relates the chips? The real power. We consume chips, that can be related as consuming real power. And we pay for the entire packet, that is the apparent power. I think it is very much clear from this analogy that we actually consume real power, right? So we are talking about the power factor. Remember, power factor was equals to that real power upon apparent power. And power factor, power factor PF, and power factor was having a range from 0 to 1. So what is considered a bad power factor? Anything below 0.85 is considered to be a poor power factor, means poor efficiency. You can think like this, that it is a poor efficient system. Poor efficiency whose power factor is below 0.85. Now, how can we fix this poor power factor? We need to increase the efficiency to reduce the cost. Okay, fixing of poor power factor. How can we fix this? We can introduce capacitive load in circuit, in inductive circuit, more precisely in inductive circuit. Let me highlight this, in inductive circuit. Then what will happen if we introduce, we can introduce a capacitive, if we introduce a capacitive load in an inductive circuit, then what will happen? It will reduce the phase difference. phase difference between current and voltage. And if it does so, that is, it reduces the phase difference between current and voltage, what will happen? The reactive power component value will decrease. It implies that the apparent power, which is the sum of real power and reactive power, it will also decrease, resulting in the power factor to increase, as apparent power is in the denominator here. Clear? This is one method. There are many other methods, but generally for beginners we can stick to this one method. Okay, so we are at the end of our presentation. Here is the conclusion. That is, why should we fix power factor? Simple, to increase efficiency. To increase efficiency. More power factor. If we have a high power factor, then we need less apparent power. So more power is drawn for doing the same amount of work if the power factor is poor. If the power factor is poor. Okay. And if it is drawing more power, then what will happen? The electrical equipment will heat up, it gains heat, and so the life expectancy of the equipment will reduce. Voltage drop also happens across the equipment, which can lead into severe short circuits, and the life of the equipment also decreases. So we always try to look at improving the power factor as much as possible. Of course, 100% is not possible. Anything power factor having values between 0.9 to 0.98 is very good. Power factor. Okay, so that is for today. Thank you for being so patient and watching till the end. Do subscribe my channel, and yeah, I will try to upload more such interesting videos. Thank you.